right, hello students, working my way through the review. We got problem 7 here, a plane and a line, and we are to find the coordinates of intersection. So what we are going to do is substitute the x, y, and z from the linear equation into the planar equation. Remember that when you have all three components equal, that they all equal t from the line. So what I mean is x minus 4 over 3 is t, y minus 1 is t, z minus 5 over 2 is t. They're all equal to the same thing. That's why you can make them equal to each other. And this allows us to rewrite each of them as x equals 3t plus 4, y equals, what would that be, 1 minus t, or negative t plus 1 if that makes you happier. Z equals 2t plus 5. And then we substitute those all into the equation pi. So 4 times 3t plus 4 minus 3 times 1 minus t plus z, which is 2t plus 5, equals 1. Now we just distribute everything out. Hope it comes out to something nice. Let's see. And collecting all my t's, I think that makes 17t plus 18 equals 1. Oh, that's great. So then 17t equals negative 17. T equals negative 1. Go back and substitute to calculate that x equals negative 3. So 3 times negative 1. Negative 3 plus 4 makes 1. Y makes 2. Z makes 3. So now we know our point of intersection is 1, 2, 3. Okay, that was pretty nice. Okay, then next up, determine the angle between the line and the plane. Okay, so when we have the angle between two vectors, we're going to want to use the dot product and the cosine formula there. One little thing to keep in mind is that the plane equation gives you the normal vector, and the linear equation gives you its actual direction vector. And so that would be kind of different by like 90 degrees. And so we'll work through that together. But basically, the plane has a normal vector of 4, negative 3, and 1. And the line has a direction vector of 3, negative 1, and 2. And that you get those just from how I solved just a second ago, how I wrote z equals 3t plus 4. X equals 3t plus 4, y equals negative t plus 1, z equals 2t plus 5. That's where I'm getting those from. They're also the same as the denominators here. Just be careful because the y is negative, and so that's why I wrote a negative 1 for the y component. Okay, so remember that the formula we're going to use is that a dot b is equal to magnitude A, magnitude B cosine theta. And so we're going to dot product those two things. So we do 4 times 3 plus negative 1 times negative 3 plus 1 times 2. That's the dot product. Let's also calculate the magnitude. So the magnitude of n is going to be the square root of 4 squared plus 3 squared plus 1 squared. The magnitude of L is going to be the square root of 3 squared plus 1 squared plus 2 squared. So magnitude of n is the square root of 26. Magnitude of L is the square root of 14. So I'm jumping around a little bit. I did not finish out my dot product, so this becomes 12 plus 3 plus 2 makes 17. Okay, so what are we at here? We know that the dot product of 17 equals one magnitude times another magnitude times cosine of theta. So it looks like cosine of theta is going to equal 17 divided by root 26 root 14. All right, so I'm going to pause for a second, grab a calculator. I do not know that cosine off the top of my head, as I hope you do not either. All right, got my handy calculator here. So we're going to do the inverse cosine of 17 divided by square root of 26. Oops. Okay, let's get that in there. Almost did something terribly wrong. Square root of 26, square root of 14. Let's see, am I in the, and I'm in radian mode. Okay. So I get that the cosine, the angle, inverse cosine is approximately 0.471 radians. Now be careful, because we didn't actually find with this the angle between the line and the plane. So just as a visualization, we had a plane going like this. This is our plane pi. We had a line L coming at it, intersecting it, and kind of going through it. This is line L. And what we actually found is the angle between the normal vector and the plane. So the normal vector has a 90-degree angle like that. So we actually found this angle. That's our angle theta right there. And so because this is a normal vector, we can draw our little right triangle, and we know that the angle that we actually care about is complementary to that. So if I was using degrees, I would just do 90 degrees minus the angle I just got. And so because I'm in radian mode, I actually want to do 90 degrees, but in radians would be pi over 2 minus 0.471. And that's going to pop out to be, what will it be? 1.099. So 1.1-ish, approximately 1.1. And so that's going to be the angle in radians between the line and the plane. Okay, so then find the equation of the line that is symmetrical to the line L with respect to the plane pi. So we need to then take our line and reflect it over the plane. And so what that means is it's going to have the same angle, but it's going to be pointing in the other direction. And let's see, so if it has the same angle but pointing in the other direction, what's the simplest way to do this? It'll have that same point of intersection that we had before. I'm going to pause for a second and just think about it. All right, so this is a fun situation. There's nothing like this in the textbook, and the textbook's answer key doesn't have anything about it. What I would do, and I'll tell you this, I will not put this question on the test, but what I would do if I were to do this is I would go along the normal vector from my line L and then travel to the other side of the plane here, an equivalent distance, and then I would find the equation of the line that connects those points like that, so that the line is symmetrical across the plane right there. So that is something that we could do, but I will tell you that we will not. We will not do that. So that would be a problem where I could take like this point up here, which is the point for -1 and 5, and I would travel along the normal vector twice. So take it, let's see. So instead, I'd go down 4, up 3, down 1, and I do that twice. So that would get me to the point -4, because I took away 4 twice, so I took away 8. I'm going to add 6, so that'd be +5, and I'll take away 2. And so that point would be on the other side of the plane, and then I can use that with my point of intersection of 1, 2, 3 to create a new direction vector. So my new direction vector would be -5, 3, 0, and then I could write the new equation of the line. And I guess that would be symmetrical to the plane symmetrical to the line L with respect to the plane pi. But again, I didn't see that in the textbook. They didn't even have that on the answer key. I will not put that on the test. But that's the best I could come up with off the top of my head. So parts A and B would be fair game. Part C, don't stress about it. But what I showed you down here is how I would approach that. So that's the direction vector. So you would just take a point on the line, such as 1, 2, 3, and then plus t times your direction vector. And there you go. All right. Thank you for watching.